Okay, so I think we're pretty close here. There might be some people hopping in, but that's okay. Um, we are flying by here. You know, I think the stuff we've done already in like 3.5 days is typically about 2 weeks during the semester. So I don't know. I keep repeating it, but it's just kind of flying by, and that's exactly what's going to be on test one. So on Monday, just remember that you can use open book. It is open book, open note, so you can use that stuff, open book and note. It's going to be on basically chapter 9. And so what I'm going to do is on Monday, we'll come together, and then if you have review questions or something like that for maybe like half an hour, here. So it'll be probably about 30 minutes, question and answer kind of stuff. And then I'll release the test, and you'll have about the test. The test itself is 1 hour, and so I've asked you to like write the start and end time on there. But you have a sort of a 90-minute window um, to to do it, and that allows you to make sure that you have plenty of time for like download, upload. You don't actually have to print the test if you don't want to. You can just write out, use it on the side and then write out answers on blank pieces of paper and then just submit those with your help receive statement. If you're the kind of person that likes to have the test right there and want to print it, then that works too. If you can get the Scan Pro thing to work, it's nice. If not, just send me the JPEGs of it. Preferably, I don't know if you can control it, but like some of the tests sideways, the homework's a little tricky to grade. So if you can at least orient it up and down, that would be great. I don't know if you can control that in Canvas or not. But so on Monday, I'll remind you of all that, but just sort of be ready for that, review the stuff. I'll get a lot of the grades down because I know that you have a lot of homework coming in. I've done the first one, and I'm still grading on completion, but I'm making some little notes for things to make sure that you correct. And so if you have questions, this afternoon or at any time, and to catch back up on those, because I'll correct as much as I can, but it's mostly for you to get practice in that. And so even if it's like 10 out of 10, it doesn't mean you got them all right. It just means that you've made a good attempt, and I'll try to give you feedback. So with that in mind, that we basically have completed chapter 9, and so that's what's on the test. But I didn't want to give you the test right away, so we're going to do a little bit of chapter 10 stuff today and tomorrow, and so that's just the way the schedule worked out. So the whole thing on chapter 10 is, possibly some stuff that you've seen before, except maybe not in 3D. So we're going to basically jump from 2D to 3D. And so how do you do a bunch of this stuff in 3D? So if you've seen dot products and cross products, I know you did that in Math 103, a little bit of that. You may have done it in statics, something like that. We're going to do some of that review on that. And then hang on just a second. Yeah, try to get maybe just a little bit more things that you haven't seen. So geometry in 3D. So as a basic, intro, we've stuck with X and Y. You can go back on the history of why we use X and Y, but we use X and Y, we want to go to 3D, then naturally we'll add a triple now. So instead of a coordinate using 2D, X and Y, it'll now be X, Y, and Z. And so it's an ordered triple. You go over X direction, go over Y direction, and then you got to figure out where the Z axis is in there. And it depends on whether you're taking a math class or a physics class, probably, that at least you have a set of axes in 2D, and the second you go to 3D, well, where do you put that third one? Well, it has to come out of the board straight at you, or out of the screen. But I can't draw that. I could draw a little point. It's like, there's the Z-axis. Well, it's hard to see. So we kind of take the whole thing and rotate the perspective on it. And so Z is coming out of the board and into the board. And this is definitely the positive Z-axis. So where I write the letters is the positive Z-axis. And this does matter in your physics classes and probably other engineering classes, that you have to maintain the right-hand rule. So if you're talking about things like torque, and you know, it's like a screwdriver for right-hand rule and the screw this way and the screw will go in righty-tighty kind of thing, is if you think about these in the three-dimensional kinematics, then you want X to point in your pointer finger, and then Y is the middle finger, and then as you move the pointer finger to the middle finger, the Z will point the direction basically of the torque, and that's going to be your thumb. So that kind of thing definitely has to be maintained. So we will sometimes do pictures like this if it is useful, or we may rotate everything, which now starts to be a little strange, but sometimes it's nice to have the Z-axis pointing up. And if the Z-axis is pointing up, again, the positive Z-axis, then you got to figure out which one of these two is X and Y, but you have to maintain the right-hand rule. So you look over here, if you rotated everything up, then this one's going to have to be X, and then this one's going to have to be Y, so that you've maintained the rotation from X to Y, and Z will be your thumb value. Otherwise, if you flipped it over, you would be basically doing like a left-hand rule, and I don't know, most people are right-handed, so I guess they just pick that. Sorry, lefties. My son's a lefty, and you know, you got to buy all the left-handed stuff, but I guess that's the way of the world. So naturally, you can talk about distance between distance in 3D. And so if you have 2 points, x1, y1, z1, and x2, y2, z2, and you want to talk about the distance from one point to the other. Well, in 2D, you can make a triangle, a right triangle that you're used to, and you can use the Pythagorean theorem. You know, a squared plus b squared equals c squared. And in 3D, I'm not going to draw the whole thing out, but it actually turns out you can kind of do the Pythagorean theorem between the first 2 coordinates, and then you can kick in another Pythagorean theorem between that and the last point. So it's sort of like 2 triangles up in space, and amazingly enough, you get something that looks very much like the Pythagorean theorem, that the distance between those 2 points, you know, what did you have before? It was like x2 minus x1 squared and y2 minus y1 squared, and then you took the square root of that to get the distance. But if you do that and then repeat it again in the z direction, it actually just expands to get z2 minus z1 squared, and then if you get the square root of all of that, then that'll actually give you the distance formula in 3D. So that's pretty cool that it expands out, and maybe you already knew that, but still, you stop and you're like, I understand the first part Pythagorean theorem, but how do you get 3 of them in there? And so you can draw the picture and you can actually see the triangle in 3 dimensions. That gives you the distance. And this is particularly nice because if you want to start to draw equations, not just for curves anymore, but for what are called surfaces. So like a ball, or you'll see, we're going to do a bunch of them here today. So we know that the definition of a sphere is all points, and in this case it's now x, y, z, that are equidistant from the center. And if you give that one a name, let's see, before we had like H, K, yeah, we'll go ahead and do it. I don't like using L, so I'll make kind of like a cursive one. I don't want to make it look like a 1 or a capital I or something like that. And when I say equidistant, I'll say of distance r away. So it's a radius, and now we can go in any direction, 3D. And so that will, all those points together would form a sphere. So what's the equation? Well, we just use the distance formula. R is the distance. So we'll get R on that side. Instead of doing x2 and x1 and y2, y1 and stuff, we use these points here. So we'll use x minus h squared plus y minus k squared plus z minus L squared. And then you would take a square root, and you would get d. But I don't really like square roots, so let's just square both sides, and we'll end up getting an equation like that. And that is the equation of a sphere. And when I say a sphere, I mean the outside of the sphere, so like the ball. So in 2D, we didn't have this last term, and we just had like x minus h squared, y minus k squared, and r squared, and that was a circle. But adding this extra piece on there gives me all the points in the sphere, like the usual. And that's not great, but it's the outer shell of the ball, and that's centered at HKL of radius r. So maybe that one's not too bad. That's the equation of a sphere. So what other kind of surfaces can we get? Well, this is where, let's see, let's try this one. If we just said x squared plus y squared equals 1, for example. Well, in 2D, if we were in 2D, this is a circle. And so we would just draw our coordinates, 1, 1, draw a circle, here's x, here's y. And so you get a circle. Now I can do the exact same equation in 3D, but you have to know what that means is when a variable is not listed. So I have x and I have y, but I don't have z. So since z is not listed, that means there's basically no restriction on z. So I want to try and draw this picture for every single z. And you'll see what I mean by that in a second here. And in this particular picture, I want to set up the axes so that the x and the y are here. It's a little bit easier for me to draw if x, positive y are there, and therefore the positive z is up. So what I want to do is I want to draw my circle at all possible z values. So if I don't even go up at all and I'm just in the xy plane, then my circle will be here. But at the same time, it doesn't restrict z, so I could go up 1 unit and I could draw the same circle at that height. And that's also going to be part of this surface. And I could do it at -1 or -2 or whatever. I would draw another circle like that. And I want it to be all of these circles all at once. And I can't really draw them, it's going to get too messy, so I just sort of connect it this way. Here. And if you continue this forever in both directions, because z is not listed, you get the outside of basically this tube. And so the fancy name for that, really not super fancy, is just an infinite cylinder. And you probably don't need the word infinite, just assume. So this equation in 2D is the equation of a circle. In 3D, the exact same equation is a cylinder. So there's a cylinder there. Okay, now I can continue with things like that before we get to the fancy ones. Suppose I just wrote x equals 0. Well, there's no x or z in that one, so we can actually, it depends on the context. If I was talking about in just one dimension, if I just had a number line for x, then if I said, that's a 1D, if I said x equals 0, then I would just get the point at x equals 0. So that would be the sort of equation or the plot of x equals 0 in one dimension. If I did the exact same thing, x equals 0, but I said in 2D, then what that would mean is, since y is not listed, I want all of the values in this plot where x is 0. And the answer in that case, is a line. So that is the line x equals 0. So when you're said, hey, plot x equals 0, you're like, well, do you want me in 2D or 3D? Context matters. So what about 3D? So in 3D, I want all of the points in 3 dimensions where x is equal to 0. So in this case, I actually want, you can draw it however you want, but I think it's maybe easier to put x on this side. So if I did that, then I want every single point in here where x is equal to 0. So all that means is I need every single point where I don't go out on the x-axis at all, which means anything in the y-z plane, just y-z coordinates, has to be included. So this is, and technically it goes out in all directions. I get the plane. I get a plane. So x equals 0 is a plane in 3 dimensions. In fact, here, you know, in 2D, it's the y-axis. Down here, you call it the YZ plane. Just for that very simple example, simple equation, x equals 0. One more like that, and then we'll get into some little bit fancier ones. So if I wrote y equals x squared, then you're like, all right, do I want 2D or 3D? Well, 2D, I already, you know, we've seen this one a million times. It's just a parabola. So it's a parabola in 2D. Well, what about in 3D? Well, there's no z listed, so I want all the points where x squared equals y. Now I gotta figure out what's the best way to label these things. I think maybe z should go here. You can try to draw it however you want her. Maybe up and down isn't too bad either. But I want this graph in every single value for z. So I need to have the parabola here. And also this parabola would work too, because x and y still satisfy this, and z is not restricted. So if I drew every single parabola with parallel to each other, then you get like a gutter, or what they call a trough, like a parabolic, like a half, not quite a half pipe, because I don't think those are parabolic, but in both directions. So in both directions. And unfortunately, in the math world, they actually call this like a general cylinder. And the one on the previous page that looks like an actual cylinder, they'll call that like a circular cylinder. And this is sort of a more general cylinder. So those aren't too bad. So we've got a sphere, we've got a cylinder, you got a general cylinder, you got a plane, and so trying to get actually a line in 3D is not so easy. So that's going to come later. We're going to do lines later. But for the remainder of this afternoon, or as far as we go, we're going to plot like six or seven other equations here, and they're a little bit tricky. So let's try this one. X squared plus y squared over 4 plus z squared over 9 equals 1. So I want every single point that satisfies this equation. And you start to look at that, and you're like, well, if the 4 and the 9 weren't there, I would get x squared plus y squared plus z squared equals 1, which is a sphere. And I've already done that. It would be a sphere centered at the origin of radius 1. But because the 4 and the 9 are there, then the y values are going to get either stretched or shrunk. The z values are going to get stretched or shrunk. So you're going to take a sphere and you're going to kind of push it in or pull it out along those axes. So if you sort of think about that before I go into the details, maybe you can sort of already see what it is. But a lot of these, they'll be difficult to see what they are. So in 3D, anytime you want to do something in a higher dimension, you drop it, try to drop it down to a lower dimension as much as you can. So what we're going to do is we're going to find these things that are called level curves. And sometimes they're called traces. In maybe just up here on the side, you probably have seen weather maps, right? Or let's not do weather maps. Let's just do an actual map. So if you see this sort of thing on a map, on a topographic map, then you probably did this in surveying, or maybe you just are hikers or something. Then this right here is a two-dimensional representation of some feature, some geometric feature. Now, this alone is not enough to tell you what it is. So you don't know if this represents a mountain or if it represents a valley, unless you were given more information. But this right here is kind of like the level curve that if you went and actually did it, so this is in 2D, you tried to draw it in 3D, it would actually look like in 3D, and then it would be a mountain that comes up, and then you would basically be doing the level curves around the mountain. And still, that's a little bit hard to see in 3D anyway. But that's the 2D representation of the 3D. So what we're going to be doing over here is we're going to be trying to do 2D representations in multiple directions and see if in our brain we can piece them back together to see what the actual region is. So this represents an actual mountain or a surface of some kind, but by looking at these cross sections or these level curves, we can start to piece it together. So here's what I mean. We want to take values of z and x and y and set them to a certain point and look at what happens when we do that to the rest of the variables. So if I look at the level right at 0, like what would this thing look like if I only restricted it to height 0? And the answer is, well, let's just plug it in. I get x squared plus y squared over 4 equals y. If I impose this z equals 0. And now we got to go back and say, well, what is this shape in 2D? And now we're back in the very beginning of the class when we're talking about conic sections. But this is the equation of an ellipse, where we're centered at the origin. So the center is at the origin, and it is stretched for x plus or minus 1 units left and right, and it's stretched for y plus or minus 2 units up and down. So we try to just draw that particular level curve in the xy plane. Then we would go 1 for x on either side, and we would go 2 for y on either side. It's kind of like if we took a slice straight through the mountain at level 0, that's what my level curve would be. So that's the starter. Now what you could do is you could just take a bunch of level curves, z equals 1, z equals 2, z equals 3, z equals 4, etc., and go back the other direction. Z equals minus 1, z equals minus 2, z equals minus 3, and then just piece it all together at my different heights, and that would give me my shape. And that's one way to do it. Another way to do it is to look at this from all 3 directions. Like what would it look like if I cut it at the level 0 for z, but also what would it look like if I cut it at level 0 for y? So look at it side to side instead of from the top down. So if that was imposed, we would get x squared plus z squared over 9 is equal to 1. And so if we did that in 2D, it's also an ellipse. So we also get an ellipse. X is stretched plus or minus 1. Z is stretched because of this 9 plus or minus 3. So I'm going to draw it in 2D, but we'll have to realize that this is the X and Z axes, not Y. So this would be 1 unit for X, and make it even smaller, and then Z is even higher, so it's plus or minus 3. I'm going to draw that one. It's kind of like slicing this object straight up and down. Remember, y equals 0 is the xz plane, so you're cutting it down the middle with the xz plane. And if you're following that, then at least if we tried again where we slice it with the yz plane, so that's where x is 0, then we would get y squared over 4, z squared over 9 equals 1. And then, same thing, you get in 2D, that is an ellipse, where y is stretched plus or minus 2, and z is stretched plus or minus 3. So if we only looked at it from the yz, then it would be 3 units up and down. And it would be 2 units left and right. So looking at it from the top, it looks like this ellipse. Looking at it from one side, it looks like this second ellipse. And turning it and looking at it from the other side, it looks like this other ellipse. And now try and put all those 3D things together, perspective in your brain or on a piece of paper. And this is where you guys are good at art and you're creative drawers. You can make a better picture than others. So let me try it on the next slide here. So x squared plus y squared over 4 plus z squared over 9 equals 1. I don't think it really matters which way you set up the axes here. So well, it doesn't matter. Z, X, Y. So everything we did for X ended up being stretched out 1 unit. So 1 unit that way and 1 unit that way. Y got stretched out 2. So it's going to come up here and hit at 2 and minus 2. And then Z got stretched out 3. So 1, 2, 3 in the Z direction. 1, 2, 3 in the negative direction. So we have to put those ellipses in this way, and then the other way, all together. So for Y and X, that. For what was the next one? X and Z, it looks like 1 on X and 3 on Z. So I got to do this kind of thing. Draw an ellipse that direction. And then the third one we had X is 0, so I'm only talking about in the YZ plane. We get an ellipse this way. And like I said, the more creative a drawer you are, the more hard to do it in 2D, because it's not a 2D object. We have to put all of those things together. And so, see if we try and do this. It looks kind of like this, and then wraps around this way, this way. I was to put in a few more level curves, kind of, and then this way. It's kind of like sort of a football shape, maybe more of a rugby ball, but it looks elliptical if no matter which direction I cut it. So we give this a whole new name here. So instead of called an ellipse, it's called an ellipsoid. So it's a 3D, kind of like a rugby ball. This is where your good spatial awareness can kick in on this stuff. So hopefully this will come from practice and drawing a lot of these. So that's what we're going to do. So again, as usual, please hop in and say, whoa, something, go back or something. I'm cool with that. And until you do, I'm going to keep going. Yeah, let's try this. Same exact thing. except one little change, which is going to throw everything off. So x squared plus y squared over 4, and then instead of plus, I'm going to subtract the z squared over 9. So it's exactly the same, except I changed that minus to a plus. So how big a change could that possibly be? Well, you'll find out pretty quick. Same deal. We look at the level curves in 3 directions. Again, you could just figure out lots of z's and just stack them up and see what this thing looks like. It's not a bad idea to do on your own. But we'll just try it. Z equals 0, y equals 0, x equals 0, and see what happens. So if z is 0, then the z term drops out, and I get x squared plus y squared over 4, which is 1, which is exactly the ellipse that I got from the last one. So x is stretched by 1, y is stretched by 2. So that at least looks the same. Now the fun part, if y is 0, I get x squared minus z squared over 9 equals 1. Now that one from section 9.1 is not an ellipse anymore. The minus side makes it a hyperbola. And instead of it wrapping back around to form an ellipse, it's going to open. It's going to open out instead of like opening in. Sort of think about it. And the same thing with x equals 0. So if x is 0, the slice will look like y squared over 4 and z squared over 9 equals 1, which is also a hyperbola. So now is where you start to get some creative drawing in here. I have to draw an ellipse in one direction, a hyperbola in another direction, and then a third curve is the hyperbola in the third direction. So let's see if we can piece all this stuff together. And I think again, I'm going to want, I think in this case I want z at the top. Yeah, I'm going to want z at the top. If you don't, it's just going to have it turned sideways, but I think it's a little easier to do it here. So, which one am I going to draw first? Draw this ellipse down. So at level 0, z is 0. I go 1 unit out on x, go 2 units out on y, and I want to draw the ellipse. So that would be what the level curve or the cross section is in that one there. I think the last one is probably the next one that's easy to draw because I can see I'm coming out of the board, not at all. And I want to draw this hyperbola here, which means I go plus or minus 2 on y, plus or minus 3 on z, and I make that box. I'm not going to draw it in because the picture is going to get cluttered enough. And then the hyperbola is either going to open left, right, or it's going to open up, down. And you just have to remember or redraw or convince yourself somehow that if the minus is in front of the y or the minus in front of the z, it opens the way you think it should. I don't know. There's lots of ways to remember that. But because I already have these points here, it's actually kind of a nice guide that I end up getting a hyperbola this way, and I get a hyperbola that way. So that one's going to come from when x is 0. This is going to come from when z is 0. So that's the first one and the last one. And now the middle one is now like the thing that's coming out of the board. X is coming out of the board. I want to go plus or minus 1 unit on x, which I already have. Again, plus or minus 3 units on z, and I have a hyperbola that's coming out of the board towards me and going into the board away from me. So now it starts to get a little bit really creative here. And this one's going to go away from me. So isn't that fun? Maybe we can just do one more here. If we said, say, z equals 3, what's going to happen at another? So if we went up 3 units in that plane, what would the cross-section look like? So we look at our picture up here, and we get x squared plus y squared over 4. This right here, if I put in z equals 3, would be 9 over 9. So that's 1. I'll be subtracting 1 and equals 1. So I'm going to just add that 1 to the other side, and so this will be equal to 2. And then if I just divide everything by 2, I'll get x squared over 2 plus y squared over 8 equals 1. And that is exactly the equation of another ellipse. It's just bigger. Because the numbers on the bottom are smaller, it makes the overall ellipse bigger. So if I went up 3 units here, and I wanted to draw that one, I get an ellipse at that height. And the same thing would happen if I went down below. I'd get an ellipse that way. And I don't know if that's starting to help what the picture looks like, but what it does look like is basically this. And it's infinite in both directions. So it's kind of like, you can think of it as like a spool, a thread, or if you've ever seen those nuclear cooling towers, it looks exactly like that. And because most of the things in there are hyperbolas, this is called a hyperbole, and not hyperbola, but we throw the letters on there, hyperboloid. It is called a hyperboloid. And there's no reason to say, well, I'll tell you what it's actually called a one-sheet hyperboloid because it's all connected together. And so that's a little foreshadowing there that, well, if that's a one-sheet hyperboloid, is there such a thing as 2 or 3 or 4 sheet hyperboloid? And, well, that'll be next. Let me do one more, and then we'll take a quick break, and then we'll come back and finish those off and then see if there's final homework questions. Okay, so this one, exact same thing. I'm going to have x squared, I'm going to have y squared over 4, I'm going to have z squared over 9, and I'm going to have 1, except I'm going to change the pluses and minuses again, where instead of plus, plus, minus, it's going to be the reverse. Minus, minus, plus. And then the question is, what's the effect on that? So let's see. Let's look at the level curves here. I'm going to start in a different order here. If x is 0, then the first term will drop out, and I'll get minus x squared, y squared over 4, z squared over 9 equals 1. And so we'll go back to the very first section of the book. That's a hyperboloid, or hyperbola. It's just now the minus is in the other one, so instead of opening left and right, it's going to open up and down. So y equals 0. Very similarly, minus x squared plus z squared over 9 equals 1. I get a hyperbola, and it also opens the opposite direction of the one that I just did. Now, there's an issue if I try and do z equals 0. So if you tried z equals 0, just plug that in, what are you going to get? You're going to get negative x squared, negative y squared over 4 on the left, and on the 1, you're going to get, on the right, you're going to get 1. Now that's a problem, because everything on the left is a square and then negated. So anything that's squared is positive, so the negative of that is going to be negative. So this is going to be negative, this is going to be negative, they're all put together as negative. There's no way to get points x and y to give 1. And so there's basically no points in that answer. So if you were to look at level 0 on the graph, you would see nothing because there's no answer to this that actually works. So that means I'm going to have to pick a different z value to figure out what that is. And I can try it again. If I tried 1, then I actually end up in the same situation. This wouldn't be 1. It would be 1 minus a ninth. And everything on the right would be positive, and everything on the left would be negative, and I would get nothing. So z equals 0, and z equals 1, and z equals 2. I get nothing because I have no answers to my equation. I have no solutions. So the first point I can actually get something is when z is 3. So I have to go 3 units up before I start hitting anything with the slice. So let's see what that looks like. Negative x squared minus y squared over 4. Then I would get plus 1, because z is 3. So this would be 9 over 9 equals 1. So if I rearrange that, I'll get x squared plus y squared over 4 equals 0. And now you look at that, you're like, how do I get x and y and plug them in there, square x, square y, divide y by 4, and somehow add them to get 0? And the answer, the only way to do that is x and y both have to be 0. So the level curve at that single point there is just the point 0, 0, 3. I like barely grazed the object. I hit it in exactly 1 point. So I have to keep going up. So say z equals 4. So I move up 1 more unit, and I look at that level curve. So this will be the last one I'll do, and I'll piece it together. So negative x squared minus y squared over 4. Now plus 16/9 equals 1. So this is okay. It's still not pretty, but I can reorganize this to make everything the same. X squared plus y squared over 4, move those to the other side. Then I could subtract 1 back to the other direction, and I would get equals 7/9. So I can rearrange this a little bit, and I would get that, in fact, that is an ellipse. So now that I'm up at level 4, the cross section is an ellipse. And at level 5, it'll be another ellipse that's bigger, and another ellipse that's bigger. And so if I try and piece all of this stuff together, just a reminder from the last slide here. Yeah, x was coming out. So I have x dot y, or sorry, z dot y. Then I need to draw an ellipse, but if I go up by 3 units, it's 2, 3, I get a single point. And I don't know if you noticed, all of these things, this could be plus or minus 3, and this could be plus or minus 4, because everything gets squared out. So I get a point 3 units up, and I get a point 3 units down on z. If I go 4 units up, I get an ellipse. If I go 4 units down, I also get an ellipse, 4 units. And if I kept going, I'd get a bunch of ellipses that are getting bigger and bigger. Now, how do I do the hyperbola? Well, I go 3 units up for z, I go 2 units for y, and I'll end up getting a hyperbola that opens up instead. So I'll get one that opens. Well, I'm actually doing the second one, but just because I screwed up the picture. So I get a hyperbolas that open up and down, and I get hyperbolas that open into the board and out of the board on the top and the bottom. And if I drew a couple more level curves, basically you can see what you'd be getting is you get a bowl, kind of a bowl shape up here, and you get a bowl shape down there together. And all of that together is a surface. And again, because all of this stuff comes from hyperbolas, we put it in here. This is an example of something called a hyperboloid. As well, but it's 2 sheets because they're not connected. So I'm going to get a bowl up here and a bowl down here, and I get, like, they call this 1 sheet and 2 sheets. And most of the stuff in there is a hyperboloid. Cross sections this way, I guess you could call it an elliptical hyperboloid, to be more precise. At least it's a hyperboloid of 2 sheets. Okay, so we've already gone from like, hey, here's X, Y, and Z to here's a hyperboloid in 2 sheets in like 30 minutes. So we'll take a quick break. We'll come back and in a couple minutes, finish a couple of these, and then just sort of see if you have any questions. So back in maybe like 4 or 5 minutes.